Okay, so now we're going to go ahead and solve some problems using the power equations. And again, the idea behind this is power is work over time, or force times velocity. And today what we're going to do is we're going to look at a variety of examples to see how to use either of those equations to help solve some problems. So here we have Wayne pulling a 305 Newton sled along a snowy path using a rope that makes a 45-degree angle with the ground. He pulls with a force of 42.3 newtons, and we want to determine if the sled moves 16 meters in 3 seconds, what power does Wayne produce? So certainly he's doing work on that sled, and the power would just be describing the rate at which he's doing that work. So first thing I'm going to do is I'm just going to use that power is work over time. And I'm going to go ahead and say, let's use work as force times displacement times the cosine of theta, where theta again is the angle between the force and displacement, and then divide that by time. And when I go through and plug in the numbers that were given to me here, I see that we get a 42.3 newtons is a force that Wayne exerts. He pulls the sled 16 meters. The cosine of 45 degrees is needed because the angle of that rope is at an angle to the way that the object is moving. And so we have to take that component as we did before. And then divide that by 3 seconds. You see the work he did is 478 joules. And divide that by 3 seconds to get about 160 watts. Now here we have another example where we're loading a moving truck. Person has to lift 25 boxes weighing an average of 60 newtons each. Vertical height that each box is lifted is about 1.3 meters. If the task takes 3 minutes, what average power is developed? Again, what I'm going to do is I'm going to use the power is equal to work over time equation. In this case, I'm going to use that work is actually just equal to the change in gravitational potential energy that the boxes acquire due to the work that I do. Now, when I go through and plug in the numbers that are given to me here, I see that each of the boxes has a weight of 60 newtons, and I have 25 of those that I'm lifting up. So the total force that I have to exert then would be 25 times 60. I'm lifting those 1.3 meters, and so that would be the change in height. Takes me 180 seconds, and I see that I do 1950 joules of work, 180 seconds of time to do that, so I develop about 11 watts of power. Now here I have a little bit more complicated of a problem. I have a conveyor belt that's inclined at 30 degrees from the horizontal, so that would be a 30-degree angle. And it's used to transport bundles of newspapers from the mailroom. So this would be the mailroom here to the cargo bay, which is up here. And so we're going to take this and we're going to deliver some bundles of newspapers. And the question is what power needs to be developed in order to deliver those newspapers at the required rate. So to do this, I see that each newspaper has a mass of 1 kilogram, and there's 25 newspapers per bundle, and there are 15 bundles that I need to lift per minute. So again, I'm going to start with the powers work over time, and just as I did on the last example, I'm going to say that the work is equal to the change in gravitational potential energy that the newspapers acquire over a minute of time. So what I'm going to do is I'm going to look at the total amount of work done in a minute, and then I'll take the ratio of those two quantities, and I'll get the power. Now when I go through and look at the total of all of the newspapers lifted up in that minute, I see I've got 15 bundles, and there's 25 newspapers per bundle, 1 kilogram for each newspaper. So when I multiply all these together, I get the total mass of newspapers that's lifted. I multiply that by 9.8 newtons per kilogram to get the weight. So this right here, mg, is really all of this. And then the height is something that I need to calculate. Now in order for me to find the height, I'm going to go ahead and use that the height is 12 times the sine of 30 degrees. This is this quantity right here. The 12 meters is that length, and since I'm looking for the opposite side there, I'm going to use the sine of 30 degrees multiplied by the 12 meters to get the height, and so that would be 6 meters. So the total gravitational potential energy that the newspapers acquire during this lifting is just mgh, and that's found by this top equation. I'm going to go ahead and plug those numbers in here. And again, I get the 15 times 25 times 1 times 9.8 times 6, all divided by 60. And when I go through that computation, I see that the total amount of work done in a minute is 22,050 joules. I divide that by 60 seconds to get about 370 watts, or about half a horsepower. So now here we have a little bit more of an industrial application, maybe working with a pumping system for oil. This one's a little bit more involved because I'm going to throw in a little bit of a density calculation here. So in 35 seconds, I have to deliver enough oil to fill a 0.550 cubic meter barrel. It's on a platform that's 25 meters above the pump intake. So I have this oil down in some reservoir. I'm going to use a pump to fill a drum or a barrel that's up 25 meters. And I'm going to do that with some sort of pumping system. And so that pumping system is just going to take that pump or that oil and lift it up. So it's doing work on that oil. Now the way that I'm going to do this, I'm going to start with, I'm going to find the work done by the pump for each barrel. So I'm going to say the work done by the pump for each barrel that I lift. And so to find that, I'm going to use work is equal to mg delta h. In order for me to get the mass, I'm going to have to use the density equation. That mass is density times volume. Now this requires a fair amount of work to get to that value, and I'm going to show you just how we can compute that. The density is 0.820 grams per cubic centimeter. If I multiply that by the volume directly, I'm not going to get good units, or the units to cancel out. So what I'm going to do is I'm going to do some conversions. I'm going to take that grams per cubic centimeter and convert that into kilograms. And so when I do that, I see that the grams reduce here and the grams reduce there, and I get kilograms per cubic centimeter. And then what I'm going to do is I'm going to convert that cubic centimeters into cubic meters. And so that's what I'm doing with this conversion factor. And you can see that those reduce then. And then when I multiply that whole thing by the volume, again that volume is the volume of a drum, I get the cubic meters to reduce with that. And when I multiply that all out, I get 451 kilograms. Now that's my mass in that equation. I'm going to go ahead and compute that the total work done then is mg times h, where m is 451 kilograms, g is 9.8 newtons per kilogram, and I have to lift those things, or lift that oil in a continuous process about 25 meters. So the total work that I have to do is about 110,000 joules to fill a barrel that's 25 meters above my oil. Now here I want to calculate the power produced by the pump. And again, I'm going to use power is equal to work over time. This is a fairly easy calculation now that I've determined the work done per drum, or per barrel. In this case, 1.1 times 10 to the 5th joules, and I'm filling a drum in 35 seconds. Again, that was a per barrel idea, and my requirement is that it's 35 seconds to do that. That just means that I have to do work at a rate of about 3,200 watts. That would require about a 4.2 horsepower motor. One more problem for us. Let's say that I have a motor, it's a 188 watt motor that's going to lift a load at a rate of 6.5 centimeters per second. I want to know how heavy that load can be. So what I'm going to do is I'm going to start with the power is equal to work over time, or it's equal to force times velocity. Again, we've used the work over time quite a bit. This one I'm going to go ahead and show you how I can use force times velocity. So in this case, since I'm looking for the force, how much load I can lift, that would be the weight of the object, I'm going to go ahead and use solve this equation for force. So force would be power over velocity. Since I'm doing work at a rate of 188 watts, I'm going to go ahead and divide that by the speed at which I want to lift that load. So that would be 0.065 meters per second. And when I go through and do that computation, what I get is about 2892 watt seconds per meter. Now, what I'd like to do is I'd like to convert this into more simple units. So if you remember, the watt is equivalent to 1 joule per second. So when I go ahead and say the watt second, if I multiply this by the second, so what I get is that this right here is actually just a joule. So that'd be joules per meter. And if you recall, the joule was equivalent to a Newton meter. So when I take the joule divided by the meter, what I get is just a newton. So this 2892 is in fact just the weight of the object that I can lift. And so the answer to this problem is that I could lift a object that weighs 2,890 newtons. It would lift it at 650 or 6.50 centimeters per second based on the rate at which it can do work. And another problem. My car has a mass of 2,100 kilograms. The total of all opposing forces acting in my car while traveling at highway speeds is about 29 meters per second. That total amount of force is about 450 newtons. How much power must my car's engine develop to continue moving at this speed? Well, for this problem, I'm going to start with a quick FBD, and I'm going to go ahead and think of that FBD as the forces acting on that tire. Now, certainly I have the weight of the car, I have the normal force acting up, and this right here represents the air resistance. So I have 450 newtons of air resistance acting against my car. Well, my engine must develop enough force by pushing on the ground, and the ground pushes forward on the car. It has to be able to balance that. So this is the force that the car has to feel forward in order to balance the force of air resistance. So what I'm going to do for this problem is, again, I choose whether or not I use power as work over time or force times velocity. In this case, since I know the force that is acting and I know how fast I'm moving, 29 meters per second, I'm just going to go ahead and determine power by multiplying force times velocity. And when I multiply those together, I get that the amount of power that my engine has to develop is about 13,050 watts, or that's about 17.5 horsepower. So I don't need an incredibly large engine to be able to move down the highway at highway speeds. This next problem is going to show you how much power I would need to develop to accelerate. So here, I'm going to go ahead and think of the car down here. It's going to go from 0 to 65 in about 12 seconds. Now, to accelerate means I need to have an unbalanced force acting on the car. I'm going to ignore any of the opposing forces. These are really small compared to the amount of force I need to have forward to accelerate. So I'm going to go ahead and try to determine the power developed by my car by either looking at work over time or force times velocity. Now this one's a little bit tricky. We might be tempted to use force times velocity because I know how fast the car is moving, but that's the final velocity. The velocity is constantly changing, and so this works really well if the velocity is a constant, as it was up here. In this case, it doesn't work too well, so what we're going to do is power is work over time. Now we still have the task of trying to determine how to get work out of this, and I'm going to recommend for this one that we use net work is equal to change in kinetic energy. And again, because we know how fast the car is going to be traveling at the end, I can just look at the change in kinetic energy to be equal to the net work done. Now when I go through and do that, what I get, I'm going to go ahead and say that power's work over time, which is the change in kinetic energy over time. That would reduce to 1/2 mv squared all over 12 seconds. And when I plug in those numbers, what I'm going to get is about 883,000 joules is the kinetic energy of that car. Divide that by 12 seconds means that my car has to develop about 73,600 watts, or about 99 horsepower. So the idea here is that I do need a significant horsepower for acceleration. I don't need a whole lot to be able to move at highway speeds, but I do, if I want to speed up at least relatively quickly, I do need to have a large horsepower. And you know that your car's engine starts to rev at much higher RPMs to be able to accelerate. And one more problem for us to look at. An archer pulls back a bow a distance of 65 centimeters in about 1.2 seconds. So I want to determine how much energy the archer expends if we treat this bow sort of like it's a spring. Now in reality it's not a spring, but it does change its shape sort of like a spring. And so when I pull that string back on that bow, it causes the bow to bend, and so I'm storing energy in the shape of that bow. So if I want to determine how much energy I expend or how much work I do, I'm just going to use EPE as 1/2 kx squared, and I'm going to go ahead and just go ahead and substitute in these values here. And about, you see, that's about 125 joules. Now if I want to determine the power that I developed during this pull, I'm just going to go ahead and use that power as work over time. I do 125 joules of work in 1.2 seconds, and I see that that's 104 watts that I develop when I pull that back. Now the bow snaps back to its original shape. When I let go of that string, it goes back very, very quickly. It only takes 0.037 seconds for that arrow to be shot out of there. So what I'd like to do is determine how much power the bow develops. Now in this situation, the same amount of work is done, but now it's the work that the bow is doing on the arrow instead of the work that I do on the bow. So 125 joules divided by 0.037 seconds is about 3,400 watts. So a significant difference in power between how much power I develop and how much power the bow develops. So I do a little bit, or develop a little bit of power, the bow develops quite a bit more. Now high power is needed to get that to go out at a very high speed. If the bow developed as much power as I did, heck, I might as well just throw that arrow with my hand instead of storing all that energy in the bow. So the nice thing about the bow is that it does that work much more quickly, which means it can speed it up. Now I have a few more topics that I'm going to discuss here, but I'm going to save this for another video because it's starting to get lengthy already. We'll talk about how to do electrical energy on the next lesson. So I'm going to go ahead and stop it there, and I will say that that you should be able to do now these problems, and we'll go over more of what the kinds of problems you should be doing in class. But this should be able to be done now based on today's lesson. So there we go. Have a good go at that, and we'll talk to you tomorrow. Go Bucks.